Well, welcome. This is another brand new series where I'm going to discuss and bring you along on my journey to understand what is a hugely complex issue that is facing all of us today, and that is the topic of climate change. Um, Honestly, I have accepted that I really don't understand it. It is very complex, and I have been so far very uncomfortable not really understanding the details and the science and the engineering behind it. So I've decided to take some time and try and understand it for myself and look into, figure out what my real questions are and take it as a task to go through and try and get answers to those questions as best I can. This is about an engineer's approach to understanding some of the basic principles behind climate change. Again, I am accepting the fact that I really don't understand it, and I'm guessing a lot of people also don't understand it really. So this is kind of, I'm going to try and be very objective in my analysis and use an engineering approach to looking at the data and analyzing it as best I can. Honestly, if you are feeling like you're going to approach this with a lot of emotion and politics, this is not the video for you. My goal here is to take an objective engineering approach as best I can to answer some of the basic questions so that we better understand it. And honestly, in this first part, I learned a lot. I had some real questions about what we're going to talk about in this first part, which is measurement accuracy. And I learned a lot. I learned that my fears were actually, or my skepticism was actually misplaced to a large extent, not totally. But so what we're going to do is try and apply some engineering principles and as best I can, try and figure out some of the things that I've always had question about. Again, we're going to try and do it objectively, non-emotionally, and with facts and data. So if you could approach it that way, then I think together we can learn something. So first, my background. I'm an electrical engineer. I've been an electrical engineer for something like 35 years. I like engineering. I like analyzing data. I like understanding. I like simulating things, getting a handle on things so that I really understand it. I feel uncomfortable when I have a technical issue that I don't quite understand. So this is my attempt to use my best engineering judgment to analyze the data I can find. Again, this is a hugely complex issue. And honestly, if you don't think it's extremely complex, I think you probably haven't scratched the surface, because if you look at some of the papers and all the different areas it covers, science and thermodynamics and physics and geology, it is a hugely complex series of issues. So again, I am not a meteorologist or a climate scientist, so I'm going to do my best to, given the time I have to analyze this stuff, to try and figure out at least some of the issues and get a better handle on them. But again, I'm not an expert in meteorology or climate science or geology. So I'm going to do my best. If you disagree and you have a better idea, then feel free to post a video of your own. Again, I'm interested in facts. I am not a politician. I'm not interested in politics or emotion or shouting or name calling. So please, that's not what this is about. I honestly don't really care about the answer other than I want to have the facts so that I understand the answer. Okay. Again, I am also, as required by the engineering profession, I'm a skeptic. I am skeptical of just about everything I don't understand. And generally, scientists and engineers, that's how we do our thing. That's our life, is being skeptical. Science and engineering are both basically inherently skeptical. You have to analyze using data and having people argue with you and disagree, and you have to use you have to look at both sides, and you have to analyze and get a bunch of people together to try and figure out the answer. Because honestly, we're all born knowing not a lot. So we have to use our best judgment and look at the data, look at the facts, and try and analyze them. And again, as an engineer, you must have a personal knowledge and understanding of stuff. You can't design something based on somebody's word and say, oh yeah, I trust what you say, and put it up and it falls down and kills people, right? You need to take personal responsibility. A lot of times you have to sign drawings with your name saying, yes, this is correct. So skepticism is part of our nature as engineers, so we need to follow our skepticism until we really understand, and we need to be objective so that we're not biased one way or the other. So again, skepticism is good. Nowadays, it's people call, it's a bad name to call people, but in my world, in the scientific world, skepticism is good, or at least it should be good. And my view is trust yet verify. So I want to look at the data and I want to understand it and be as unbiased as possible. So again, I'm not comfortable with my knowledge. I'm totally happy to admit that I don't understand this very well. It's extremely complicated. So if you're interested in hopefully learning a little bit more, please, I encourage you to join with me, and maybe we can learn a little bit as we go along. So where do we start? What I'm going to do is I'm going to take this graph, which is the National Oceanic and Atmospheric Administration Temperature Anomaly graph, and I'm going to look at it from an engineering, at least my engineering perspective, and see what questions I have and what I need to answer. This is a graph. The title is The Departure of Global Temperature from the Average between 1880 and 2018. So as an engineer, the first thing you do when you look at a graph is you look at the X and Y axes, all right? So on the X-axis, clearly it goes from the year 1880 to 2018. This was produced just recently in February of 2019, and it represents up to last year, which is 2018, the temperature anomaly of the Earth since 1880. Now, what is an anomaly? Well, you can see from the title, it's departure of global temperature from the average. Okay, so there are two numbers here we're looking at. One is global temperature, and that's a yearly global temperature, from the average, which means somebody computed an average of temperatures that they're comparing the yearly global temperature to. All right, so there's two numbers. There's two temperature numbers that we need to figure out here. Now, the average is, from what I found in the documentation, NOAA documentation, the anomaly is, the average is an average of the global temperatures measured in a 30-year span. And that 30-year span is somewhere between 1940 and 1970. It varies depending on who's making the measurement, but I think it's generally in this region here. They are calculating the Earth temperature for those 30 years and averaging it to get one number. Now, from what I've found, the 20th century global average, so over the 20th century, they've come up with one average number of all the global temperature readings. The one number is about 52 degrees Fahrenheit for the 21st century or 20th century global land temperature measurements have averaged out to about 52 degrees Fahrenheit. All right, so I'm guessing this average they're talking about, the 30-year average, is somewhere also in that range of 50-something degrees. All right, so this anomaly is comparing the global Earth temperature for a given year with that average of, say, 50, let's call it 52 degrees. All right, so for example, in 2018, what this says is the global temperature departed from that 52 degree average by 1.4 degrees positive, which means the global temperature, average temperature in 2018 was 52 plus 1.4, which is about 53.4, okay? So that's all this is saying. Each year is compared to that 52 or whatever average, and here's the departure from that average, all right? So that's what the anomaly is. And you can see on the y-axis, I've got it in Fahrenheit, and I've also got it in centigrade over on the left. Okay, so this shows us the change in yearly global temperature versus a 30-year average. Okay, now, if you look at this as an engineer, you see this y-axis, and I think most engineers will look at this and say, okay, what they are doing is they are discriminating between yearly temperatures with an accuracy of about 0.1 degrees Fahrenheit. Okay, so for example, here in 1965 or early 1960s, clearly they are saying that the temperature is somewhere less than or equal to minus 0.1 degrees Fahrenheit, which means they had the ability in those years to discriminate between 0 and 0.1 degrees Fahrenheit. So they had a 0.1 degree or better accuracy in temperature measurement in measuring the entire global temperature, all right? And you can see that applies even in late 1930s. So what this graph is telling me is that there is a belief that since 1880, there has been the ability to measure the entire global temperature with an accuracy of plus or minus 0.1 degrees Fahrenheit. Okay? And that has been the capability since 1880 to get a global temperature with an accuracy of 0.1 degrees. Now, as an engineer, off the top, that seems to be a very, very challenging, if not impossible task to get an accuracy that close since 1880, okay? And that's, of course, that's based on just my background and probably some bias in what I expect for temperature accuracies. But it seems like that's a challenge. So that's my first challenge, to try and understand how we can have an accuracy back in the 18 and 1900s, at least, and even here in the later decades, of 0.1 degrees Fahrenheit. So we're going to, as part of this part one, we're going to look at what are the actual accuracies of some temperature measurement devices, and whether that is a reasonable, and how can we come to that conclusion that that's a reasonable accuracy to measure. Okay, so that's the first thing I have to understand how you can get a 0.1 degree accuracy for all those years. All right. The second thing, kind of related to that, is back in 1880. My perception is, and it could be an incorrect bias, that back in 1880, what they were using to measure temperature is what some of us are familiar with, which is a mercury or liquid thermometer, which requires, it's a thermometer where the level is shown with gradations in the glass, and somebody has to go and look with their eyes and look at the temperature each time they do a reading and figure out whether it's 52.0 or 52.1, and write that down on a piece of paper and keep it in a log. So while we may have digital measurements that are more accurate in the later years, that seems to be even more of an issue with me back in the 1800s, whether you could get that kind of accuracy based on human measurement of a thermometer and writing it down on a piece of paper. So I'm not saying that my assumption is correct. It's probably totally incorrect. It's probably based on just an unknowing bias, but I need to look at that data and figure it out. So those are two big issues. There is also a third issue that is implicit here, and that is the fact that it is a global temperature, all right? If I think of global temperature, I visualize having a uniform distribution of measuring devices around the globe that existed since 1880, all right? So did we have a sufficiently uniform distribution of temperature measuring devices with the accuracy we need around the world since 1880? Now, keep in mind, at least from my perspective, In the ocean, did we have those monitoring devices in the middle of the ocean? Did we have it in Antarctica? Did we have it in the outer reaches of northern Russia? Did we have it in the Saharan desert? So those questions are my basic big questions about this. And without having answers, I find it hard to understand and to accept any answers. Now, again, I could be totally wrong about my skepticism, and there could be good answers, and I'm totally open. And actually, I'd feel a lot better if I had clear answers. And as part of this, we're going to, at least I'm going to find out that some of my skepticism was misplaced and wrong, at least to a large degree, about the accuracy question. So this has turned out so far for me to be a very interesting and learning experience. So I encourage you to stick with it, and maybe we can learn some more. So those are my big questions. My big questions and the tasks that I have ahead of me to try and figure this out, to be confident that I understand a little bit more. I need to understand accuracy, and I need to understand coverage on a global scale, because those are my big issues right now. And I also need to understand the concept of average global temperature. How doable is that? How possible is it to come up with that number, like 52 degrees for the average global temperature, to bring all the temperatures down, considering that temperatures are always changing and there are so many variations. Is that actually a thing? Okay. And then finally, well, not finally, but at least in this series, my other big thing is predictability for future decades. Okay. The implication is that since this graph shows a trend since the mid 70s or earlier of an increase in global temperature up to about, right now we're at maybe 1.6 degrees above this 30-year average. Is that going to continue? So that brings the question of predictability. And as an engineer, I think most of us are very skeptical about our ability to predict anything, unless we can put it in a lab and test it and we're absolutely certain of how it responds. With stuff that we have to predict for future decades or generations, that is very difficult for, I think, many engineers to comprehend and to understand. So these are the big questions. This first part, we're going to talk about accuracy and try and resolve some of our concerns about accuracy. So if you're interested in learning a little bit more, I encourage you to stick with me. The next part, I'm going to talk about, hopefully do a deep dive into what I can find about accuracy of temperature measuring devices and how that can all come together and give you, actually, even if you've got relatively inaccurate devices, you can get an accurate temperature reading. So I encourage you to stick with this, and if you like it, hit the like button, and of course subscribe so you can get notified of when the next part of the series comes out. Thanks a lot, take care, and have a good day.